In this video, I'll be talking about the Kiwi-Drive which is a type of holonomic-drive train. Now we're going to talk about holonomic drives. Holonomic drives are true omnidirectional drives, which means that they can move in any direction. A Kiwi-Drive is a three-wheeled omnidirectional drive, which means that it can move in any direction with three wheels. The wheels are also 120 degrees away from each other. Here's a simple diagram of what the Kiwi-Drive looks like. Now we're going to build the Kiwi-Drivetrain. Because there aren't any available parts that allow us to attach components at 120 degrees, we'll have to create our own custom part. We created our custom part using Fusion 360. Now we're going to cut the custom part using a CNC machine. This custom part will be cut 2 times, so it adds extra support when we attach the other components. Now that we've finished cutting the custom part 2 times, we will start attaching the other robot components. First, I'm going to attach 3 GoBuilda channels to our custom component, and then attach a GoBuilda plate on top of it so that we can attach our rev hub and battery. Then we want to attach 2 dual block mounts to each of the 3 channels, so that we can attach our second custom component to it. After attaching our dual block mounts, we want to now attach our custom component to it. Then you want to attach 3 quad block pattern mounts to the ends of the 3 channels so that we can attach our motors. After attaching the quad block pattern mounts, you can then attach 3 GoBuilda motors. For the Omni wheels, we'll need to have a motor shaft hub attached to them. Now we're going to attach each of the wheels to the motors. Finally, after attaching our rev hub and our battery, this is what the final product should look like. So I'm going to first talk about forces. Forces have a direction and a magnitude. Forces in the same direction can be added. Forces in opposite directions can be subtracted. And here are 2 examples. Forces can be broken down into a horizontal and vertical component. If we have a force F at an angle theta, the horizontal component would equal to F cosine theta. The vertical component would equal to F sine theta. For example, if we have a force at an angle of 60 degrees, the horizontal component would equal F of 1/2, and the vertical component would equal F of square root 3 over 2. Now I'm going to talk about torque. Torque is the turning force. For example, a turning force can be used to unscrew a nut. Torque is equal to force times distance. Looking at the diagram, the torque of F around point A is F times D. So how do we make our robot move? We must have forces in the direction of motion. For example, in the diagram, we want our robot to move in a direction parallel to F1, so F1 has to be positive. Forces perpendicular to the moving direction must be 0. So in the diagram, F2 must be 0 for the robot to move in the direction of F1. And finally, the torque must be 0 so that the robot doesn't spin. So how do we make our robot rotate? To do this, our torque has to be greater than 0, and both F1 and F2 have to be 0. Torque will be applied in the direction that the robot rotates. This is a diagram of the Kiwi-Drive. that shows the angles of the wheels. I use the fact that the angle between each arm of the Kiwi-Drive is 120 degrees to then calculate all of the angles. A note is that we are defining the length of each arm as d. We want our Kiwi-Drive to move in the y direction. I have named the top wheel to be A, the left wheel to be B, and the right wheel to be C. We are first going to set the force of wheel A to the value of 0. To move it in the y direction, we need to only have forces that go in the y direction. So we are going to turn wheels B and C in opposite directions to have both vertical components point in the y direction. This will result in a net value of f of square root of 3 in the y direction. The horizontal components that point in the x direction cancel out because they point in opposite directions, resulting in a value of 0. The torque will also equal 0 because wheels B and C turn in opposite directions. This is the code to move the robot in the y direction. We're going to set the value of the joystick equal to one of the motors, and the other motor will be set to negative the value of the joystick. We want our Kiwi-Drive to move in the x direction. This time we are turning wheel A. To make sure the robot doesn't move in the y direction, we are going to spin wheels B and C in the same direction. This will result in the vertical component forces to cancel out and equal 0. However, we have a problem now because the torque doesn't equal 0, since two wheels are moving in the same direction while the other wheel is moving in the opposite direction. In the x direction, if we set F equal to Fa over 2, the torque becomes 0, and the total x direction equals 3Fa over 2. This will allow the robot to move in the x direction. This is the code to move the robot in the x direction. Motor A will be set to negative the value of the left joystick. The motors B and C will be set to 1/2 of the value of the left joystick. Now we want our Kiwi-Drive to rotate. To do this, we want to turn all of our wheels in the same direction. This will result in the forces in the y direction and x direction to cancel out, resulting in only a torque of 3Fd, so the robot will spin in place. This is the code to rotate the robot. We're going to set each of the motors equal to the value of the right joystick. This is the code to combine the x direction, y direction, and rotation code. We use the value of left stick y to set the power for the y direction. We use the value of left stick x to set the power for the x direction. However, since the y component force is F square root 3, and the total x component is 3F over 2, we multiply the y motor power values by square root 3 over 2 to normalize the forces. We use the value of right stick x to set the power for the rotation motion. When we add all these values, the magnitude of some motor power values may be greater than 1. We then have to check if any of these values is greater than 1 and scale everything down by the greatest motor power value.